Okay, let's talk about definite integrals. We're going to start by talking or defining a Riemann sum, something that we have already been looking at essentially. So what is a Riemann sum? Riemann is the name of a mathematician who gets the credit with these summations. And these are nothing more than really the sum of the rectangles that we've been doing to estimate the area under a curve. So let f be some function defined on an interval from a to b. Partition, remember this is the word that we use when we're breaking up the interval from a to b into sub-intervals, if you will, or slices as I call them. The partition will be of the interval AB into n subintervals. And initially, we're going to talk about equal width, right? So if they're equal width for each subinterval, we take the length of the interval, which is b minus a, and divide it by the number of subintervals. Now, if, and this is a new notation here, x sub I star, it's a little asterisk or star. This is the notation we use for any point in the ith subinterval, okay, for I equal 1, 2 to n. I'm going to explain all this in a minute. Then here is the Riemann sum. It's simply for each subinterval, we will determine the height essentially. I'll put that in quotes a little bit, but the height of a rectangle by evaluating the function at this x sub I star on the ith interval times the width, right? And then I'll do the same thing for the second subinterval and the third and the fourth, all the way to the last or nth subinterval. Now, this is summation notation, right? The capital sigma means summation. We're summing from I, which is what we call the index of summation. I starts at 1 here and ends at n. And so this increments by 1, and that's what this essentially this essentially is the same thing as what we have over here. When I is 1, I got f of x sub 1 star times delta x. Then when I is 2, I've got this one. And when I is 3, the next one, and so on, all the way to when we stop where at I equal n, we get this one. And then we add them all up. That's what the summation means. Okay, so that's a Riemann sum. Now, we have been talking about these. Really, we called the if the x sub I stars are the right endpoints of the subinterval, we call this a right Riemann sum. And I use this notation where R, of course, stands for the right endpoint being used to determine the height of our rectangle, and the subscript n is the number of subintervals. We have a left Riemann sum, and I designate that L sub n if x sub I is the left endpoint of the ith subinterval. And then we have a midpoint Riemann sum, M sub n, if x sub I is the midpoint of the ith subinterval. For the right-hand sum, or the right Riemann sum, the x sub I stars are just a plus I times delta x. For the left-hand sum, the x sub I are a plus I minus 1 times delta x. Okay, let's look at a little picture of what we've been doing. Sort of put all these things together. Here's the graph of a function f. And suppose on the interval from x equal a to x equal b, we want to do a right Riemann sum with 4 subintervals. So I've divided the interval into 4 subintervals. Each has equal width delta x. Okay, of course, the delta x would be whatever the length of the interval is, b minus a divided by the n, as we said, right? That's this quantity right here. Now, what about these x sub I stars and more importantly, the x sub I minus 1 to x sub I? What is this all saying? Well, here's the notation we're going to use. We're going to start with a, the left endpoint of our interval. I'm going to call that x sub 0. Okay, and then the next point, by the way, the book calls these grid points, all these points that designate the subintervals. The second grid point will be x sub 1. The third one will be x sub 2. The fourth one, x sub 4. And the fifth, sorry, 1, 2, 3, fourth one, x sub 3. And the fourth one, x sub, sorry, the fifth one, x sub 5. I'm getting all tongue-tied here. But you see, we did that so that we end at B being x sub 4, right? And that's going to be, if it's R sub 4, if n is 4, we will always end with x sub 4. So if I have 4 subintervals, I have 5 grid points. I always have one more grid point than subintervals. Does that make sense? Okay. So when we say um, this is the first subinterval from x sub 0 to x sub 1. So our first subinterval is from x sub 0 to x sub 1. The second subinterval is from what? X sub 1 to x sub 2. X sub 1 to x sub 2. And the third subinterval will be from x sub 2 to x sub 3. All right, you get that dot, dot, dot until in this case, the fourth subinterval. Well, I guess we don't have to do dot, dot, dot in this case, but fourth subinterval will be x sub 3 to x sub 4, right? So we're ending there. So that's what this thing is. Notice the pattern. It's going to be x sub I minus 1, comma x sub I for I equal 1, 2, 3. So notice for the first, it's x sub 0 to x sub 1. So if I is 1, we can do x sub I minus 1 and then comma x sub I, right? So this would be when I is 1, this would be I is 2, this would be I is 3, and this would be I equal 4, right? Those are how we're using this notation. So the x sub I star then is some point on this subinterval, and it can be any point. It could be random, as long as it could be the left endpoint in the subinterval, the right, the midpoint, or any point in between. Doesn't really matter. Now, in the particular case where we use all right endpoints, we call that the right Riemann sum. We use all left endpoints, call that the left Riemann sum, and so on. And why are the right-hand endpoints a plus I delta x? Why is that? Well, look at the first one. The first subinterval is from x sub 0 to x sub 1. So notice x sub 1 star would be what? Whatever a is plus the width of our interval, which is delta x. And that's going to be x sub 1 star will be a plus delta x. What about the second subinterval? All right, x sub 1 to x sub 2, our right-hand endpoint is x sub 2. How do we get x sub 2? Well, it's a plus 1, 2 delta x, right? So it's a plus 2 delta x. X sub 3 star would be a plus 3 delta x, and so on. In general, x sub I star is a plus I delta x. So that's where we're getting that formula for the right-hand endpoints. And that's the one we'll use mostly when we're doing these calculations later. Now you can also do left-hand sum. Notice we have to shift back one basically, so that when I is 1, I get a plus what? 1 minus 1 is 0. I just get a. That's the left-hand endpoint for the first subinterval, right? X sub 0 or a. The second subinterval will be x sub 1 to x sub 2. I need x sub 1. And so when I plug in I equal 2 here, I get a plus 2 minus 1 is 1. I get a plus delta x. So it sort of shifts it back one, so I get all the left-hand endpoints. And there's a formula for the midpoints, but I'm not going to worry about that. We usually don't use midpoint sums when we're evaluating these Riemann sums for n. And we'll talk about that. Okay, so let's just review first of all, what is L sub 4 for the function f of x equals 1 minus x squared on the interval from 0 to 2. Okay, so I'm going to show you that. Of course, L sub 4 is what? The left Riemann sum, where n is equal to 4. So here is the graph of this particular rough graph of this function. 1 minus x squared here. It's a parabola opening downward. At 0, if I plug in 0, the value is 1. If I plug in, if I plug in 1, this is x equal 1 here, I'll get 0. And if I plug in 2, 1 minus 2 squared, 1 minus 4, I get negative 3 down here. So there's that parabola. Now, what's our delta x? What's the width? Well, or of each of our subintervals? Well, the length of the interval from 0 to 2 is, of course, 2. 2 minus 0 is 2. And we have 4 subintervals. So 2/4 or 1/2, right, is our width. So what would our grid points be? We start at, we're going from 0 to 2. We start x sub 0 is 0. And then I just add delta x to get x sub 1. And then I add delta x 1/2 to get x sub 2. and then add a half to get x sub 3, and then add a half to get x sub 4. And we stop there, right? Because n is 4, and we should check and make sure that we get to 2 when we get to x sub 4, which we do. So L sub 4 is just going to be the f of x sub I star times the delta x's. Notice there's a delta x on each one of these, so I can factor that delta x out. And then I have f of what? X sub 0, because that, again, is the left-hand endpoint, right, of the first subinterval, which goes from x sub 0, remember the subinterval x sub 0 to x sub 1, so it's the left-hand endpoint there. The next subinterval, left-hand endpoint, is x sub 1. For the third subinterval, the left-hand endpoint is x sub 2, and then x sub 3. So now we just evaluate this function, right? What's x sub 0? It's 0. Plugging in 0, I get 1. F of 0 is 1. F of x sub 1 is f of a half. And if I plug in a half, I get 1 minus 1/2 squared. That is 1 minus 0.25, which is 0.75. F of x sub 2 is 1. Plugging in 1 gives me 0. And then f of x sub 3, we're going to talk a little bit about this, is 1.5. If I plug in 1.5, 1 minus 1.5 squared, I get a negative number. Okay. So I've kind of, we're going to talk about net area here in a minute. But obviously, when I'm doing the evaluation of the function, I'm going to get some negative number. And when I take the width times the f of x sub 3 in this case, I get a negative number, right? A positive times a negative gives me a negative. So how's that going to come into play in these Riemann sums? And we'll talk about that. As far as the math goes, I add all these up, I get 0.5 multiplied by 0.5. That's the actual value I get for L sub 4. Okay, so we did these things before. We just didn't call them Riemann sums yet when we did them. Okay, so this leads us to net area. So when we look at this thing, I kind of labeled one region as positive and one region as negative. So what's all this about? Well, consider the region R bounded by the graph of a continuous function f and the x-axis between x equal a and x equal b. The net area of this region is the sum of the areas of the parts of R that lie above the x-axis minus the sum of the area of the parts of R that lie below the x-axis. So that's the definition for net area. So essentially the net area for the function 1 minus x squared from 0 to 2 is going to be what? From 0 to 1, the graph is above the x-axis. So whatever the area of this region is, that's going to be positive area, basically. And then from 1 to 2, the graph is below the x-axis. So between the x-axis and the graph, that area, the net area would be this area minus this area. Or another way of saying is this area above the x-axis is positive area, and this area down here we quote unquote is negative area. And so we combine. So net area for a function on a given interval, notice, could be close to 0. Like if these two areas are roughly the same, we could be close to 0. So it could be 0, could be a negative number, it could be a positive number, it could be any real number. So we need that definition. And in a sense, then, the Riemann sum is an approximation for the net area of the function on the interval. Now, the Riemann sums can be generalized by allowing subintervals to have varying widths. The book calls this a general partition. So in this case, the width of the ith subinterval is delta x sub I. I mean, what would the width be? It would just be the right-hand endpoint minus the left-hand endpoint. Excuse me. So notice the only difference is the x sub I. Each subinterval can be different. So we have a potentially different width in each case. And notice our summation has the delta x sub I is the only change from what we had before. So that can be true. So some intervals can be wider than others. All right. Now let's define integrable functions. Easy for you to say, right? Integrable functions. If we define delta to be the maximum of all these varying widths. Now keep in mind, if we do use widths that are subintervals with equal widths, all these would be equal to one another. Delta x of 1 would be equal to delta x of 2 all the way to delta x of all equal. And then delta would just be the same as that width. But know either way that as delta goes to 0, then the widths of each subinterval have to go to 0. Okay. And so here's the definition for a function to be integrable. A function f defined on the interval from a to b is integrable on this interval if the limit as delta goes to 0, this delta is the maximum of all the widths, so just think about the largest width that is going to 0 on this subinterval of all these subintervals. So all these, and of course that means all the widths are going to 0. And here's our Riemann sum, right? Our generalized Riemann sum with the delta x of I. So if this limit exists and is unique over all possible partitions of this interval, so any way I break it up, um, and all choices of x of I on a partition. So the x of I could be the right endpoints, left endpoints, midpoints, or any point on each subinterval. It could be just totally random. So overall, then uh, if this limit exists, then we say the function is integrable. And this has a corollary to, if you remember calculus 1, we had a similar situation where a limit was involved in determining if a function was differentiable, right? If the derivative exists, if the limit exists, the function was differentiable. Well, now we're calling this number, the limit of this number, well, we're going to call the limit of this number a special thing here in a minute, but if this limit exists, the function is integrable on this interval. Now, what is this number if it exists? And keep in mind, there are cases where limits do not exist, and so, not all functions are integrable. But this limit, if it exists, then is the definite integral of the function f from a to b, which we write this way. And so you can see this is like the indefinite integral, except we have these a's and b's. These are called the limits of integration. Okay, so the definite integral of the function f of x from a to b is equal to this limit. Therefore, the definite integral from a to b is a real number. It could be 0, it could be negative, it could be positive. And in a sense, what we see is, based on our analysis for the net or definition of net area, that's what this integral represents, the net area of the function on the interval from a to b. Now, so keep in mind the indefinite integral, that always became a function, or more importantly, a family of functions, right, with our plus c. Uh, and that gives the antiderivative of the function. There is a connection between the definite indefinite integral that we will see when we talk about the fundamental theorem of calculus soon. Now, terminology notes, we've already seen this integral sign, this elongated S, and it essentially is that. It's an elongated S, meaning this is a sum. This is a sum. It's just really a sum of what? We're letting the widths of each of these subintervals going to 0. We're getting more and more rectangles, if you will. The widths are getting closer and closer to 0. So we're getting an infinite number, approaching infinity, slicing it up into infinitely thin rectangles, and then adding them all up. So that's the process that's going on. So it's essentially a summation process. The function f of x, again, is called the integrand, right? The f of x. A and b, as I said, are the limits of integration. A is the lower limit, and b is the upper limit. That makes sense. The process of evaluating the integral is called integration. Now, we talked about integration being the word we use for finding the antiderivative. And again, you'll see why that's the case when we get to the fundamental theorem of calculus. Now, the dx symbol, of course, tells us the variable of integration, or dummy variable, is x. So keep in mind this expression here would be the same as the integral from a to b f of t dt, which would be the same as the integral from a to b f of u du. Any variable you use, right? You wouldn't use a and b in this case. Those are reserved for the constants for the upper and lower limit. But any variable, these are all the same. Okay, doesn't matter. Now, The above definition, as we said, can be simplified with subintervals of equal width, and that's the way we're going to typically do it. We're not going to do the varying widths thing. So up here, when we talk about delta being the max of all these things will be equal, and so delta will just be that width. And in that case, what's happening is delta goes to zero. We can just replace that with the limit as n goes to infinity, right? So as we have more and more rectangles, what's happening to this expression? Fixed value b minus a over n, that expression is going to zero as n goes to infinity. So that will guarantee that we are our subinterval widths are going to zero. The definite integral, if it exists, is the net area bounded by the graphs of f and the x-axis on the interval from a to b, and that's real important that we understand that. So essentially, again, what the definite integral represents is the process of slicing the regions bounded by the function and the x-axis into infinitely many small slices, and then summing these slices up. The textbook calls this the slice and sum method, and we do it all the time throughout this course. Okay, so let's just see if we understand the notation that we talked about in this for the definite integral. If I had the limit as delta goes to zero, the summation I equal 1 to n of this thing, then what do I have? Well, notice up here that the thing we're adding is f of x by star, right? And so if this is the limit of a Riemann sum for the function on the interval from 1 to 3, identify the function. Let's do that first, identify the function. Well, if this is f of x I star, then the function f of x is simply 4x squared minus 7x plus 5, right? Because if I replace x with x by star, I get this. So that's the function we're talking about. Express the limit as a definite integral. So this thing is equal to what? So let's go back up here. This thing is equal to this, all right? So it's the definite integral from a to b. Well, what is a and b? I don't have that information by looking right here, right? What is a and b? Well, we're told on the interval from 1 to 3. So this is the value of a, and this is the value of b. So this will be the integral from a to b, and it's f of x, which we just saw was 4x squared minus 7x plus 5. And then don't forget the dx tells us the variable integration is x. So this is the definite integral. This is the limit definition of this definite integral. Now, what does the definite integral represent geometrically? Answer, this is the value of this definite integral. The value of this limit is the net area for this function, 4x squared minus 7x plus 5, on the interval from 1 to 3. Okay. All right. So let's take a look at evaluating the definite integral. The first way we're going to do it is interpreting it as a net area and looking at it geometrically. Okay. So let's do that with this first one, the integral from 1 to 5 of 2x minus 4. So what I'm going to do is, first of all, sketch a graph of this function. The function is 2x minus 4. And what will this function look like? The graph of 2x minus 4 is a line. So here's 1, 2, 3, 4, 5. Okay, we'll just do that. So on the interval from 1 to 5, of course, but the graph of 2x minus 4 is a line of slope 2 and y-intercept negative 4. So at 0, right, it's down here at negative 4. By the time we get to 1, what is it? 2 minus 4, it's at negative 2. Negative 2. If I plug in 2, 2 times 2 is 4, minus 4 is 0, right? And so on. Plug in 3, I get 6 minus 4, it's equal to 2. And so on. Eventually, I'll get up to plugging in 5, what? 10 minus 4, I'm going to get 6. And so this height here, give me a second to this. And we have this line. Okay, so it is on the interval, though, from 1 to 5. So what happens? X equal 1. Let's just sort of go down, right? Because the graph is below the x-axis. So between 1 and 2, the graph of 2x minus 4 is below the x-axis. And then we're going all the way to 5, right? 2 to 5. Well, what do we have then? This region down here, let's just shade that in red. That's going to be a net area that's going to be negative, right? Remember, values below the x-axis we subtract, right, for net area. And so what is this region? Well, it's negative, and then it's a triangle, right? Triangle is 1/2 base times height. What's the base? From 1 to 2, that's 1. And what's this height going to be? Well, remember the value of the function at 1, 2 minus 4 was -2. So this length is 2, right? Don't say -2. I mean, the negative is taken care of right here, right? So, I mean, if you say it's -2, that the whole thing becomes negative. So 1/2 times 1 times 2 is, of course, 1, but we get -1. In other words, this area of this triangle is 1 square unit, but we're going to treat it as being negative. Now, from 2 to 5, we have this region here, and this region here is going to be, positive area for the net area. And it's a triangle as well, and it's 1/2. The base is from 2 to 5. That's a height of 3, or a width of 3. And then remember plugging in 5 into our function. So again, this is the function, 2x minus 4. If I plug in 5, I get 10 minus 4, I get 6 is the height. And so 1/2, 3 times 6 is equal to 1/2 of 18, which is 9. And so what's the value of our definite integral? It's the net area, right? Which is this region here, -1, plus the +9, which gives me, of course, 8. So that is the value of that definite integral. It's 8. Let's look at the next one, the integral from -3 to 2 of the absolute value of x. Does everyone remember what the absolute value of x graph looks like? At 0, it's 0. At 1, it's equal to 1. At 2, the absolute value of 2 is 2, and so on. In fact, it's basically like the line y equals x for values of x that are greater than 0. What about negative values? Well, -1, what's the absolute value of -1? Answer, +1. -2, what's the absolute value of -2? Answer, +2, and so on. So we get this familiar, hopefully, V shape, right, for the graph of the absolute value. Okay. And so where are we going from? The lower limit is -3, upper limit is 2. So at -3, of course, our height would be equal to 3 to 2, right, where the height is equal to 2. And so from -3 to 0, what do we have? A triangle. The graph is above the x-axis, so this area will be counted as positive area. And so we're going to get 1/2. The base is 3 and the height is 3. For this triangle here, right? It's also trapped above, the graph is above the x-axis, so it's a triangle, base is 2, height is 2. So we add both of these. So it's just area of these two triangles. And I get 3 times 3 is 9, half of 9 is 4.5. And then half of 4 here is 2, and I get 6.5, right, is the square units for the net area, and that gives us the value of this definite integral. Now, those are pretty easy when they come out. The regions come out as triangles. If you had a constant function, for instance, you could get a rectangle or a square, find the area of those. There's a little more complicated one here. What's this one? The integral from 3 to 4 of this function. Oh my gosh, what's that look like? Let's just take a look at this. Let's call this function y. Okay, and then let me square both sides. And then let me add the x minus 3 squared. And so what is this the equation of? Well, you should recognize that this is the equation of a circle. In general, a circle with center at h comma k and radius r uh, is given by this equation. This is the standard form for the equation of a circle, right? So you should remember that. In this case, then what is the center of our circle? The value of h is 3. So this is a circle with center. H is 3. What's the value of k here? Well, it's y by itself. What's k? Well, k must be 0, right? Y minus 0 is y, and so k is 0. So there's the center. And what's the radius? The radius r squared is 1, so r is 1. Okay, so that's what we have almost. This is the equation of a circle with centered 3 comma 0 radius 1. This function is actually the graph of the top half of that circle, y. If I'm solving for y going backwards, if I go back here, I subtract the 1 minus, or subtract the x minus 3 quantity squared and get this thing. And then I take the square root. But when I take the square root, what it's always what? Plus or minus, right? The positive root will be the top half of the circle. The negative root will be the bottom half of the circle. Since we have the positive root, we just have the top half of the circle. So let's graph this function now. So it's a circle of radius 1. The center is at 3 comma 0 right here, and the radius is 1. So go over 1 unit in either direction, go up 1 unit, go down 1 unit. That would be the entire circle. Let me just do that dashed line. But remember, we only have the top half of the circle. So the graph we're talking about is simply this. That's it. Now let's go to this thing. We're integrating from 3 to 4. So this is 1, 2, here's 3, and here's 4. So notice from 3 to 4, we're just talking about this region under this curve. Let me shade in that area. Notice it's above the x-axis on that interval, so we're going to have a positive area. And what is that area? Well, it's 1/4 of the entire circle. So the area is 1/4 the area of a circle, and the circle's radius is 1. Remember, a circle is pi times that radius squared, pi r squared. Of course, 1 squared is 1, and I get 1/4 times pi, or pi fourths. And that is the value of that definite integral. Okay, so that's how we evaluate definite integrals using geometry. Uh, let's just play around with this idea this way. Suppose that I have this function here, and um, areas of the regions bounded by its graph and the x-axis are given, and then we're going to find some definite integrals. So this function is on the interval from A to D here. So we've got A, B, C, and D, important points where the graph crosses or touches the x-axis. So from A to B, the graph is above the x-axis, and this shaded in area is 28 square units. From B to C, this shaded in region here is 7 square units, and from C to D, the area is 10. So what would the integral from B to C be? From B to C be? Well, remember, it's net area, so it's not going to be 7. It's going to be what? It's going to be -7 because that area is below the x-axis. What about from A to C? Well, A all the way to C, areas above, we're going to count as positive, and then we're going to subtract the area below, and I get 21 for the net area, right, of this function. So we're just finding net area. And then what would it be from A all the way to D? Well, obviously, I'm going to have the areas above, which are 28 plus 10, and then subtract the 7. And so I'm going to get 31 as the area from A all the way to D. And so we can do those sort of problems as well. Okay. Now we have some properties of definite integrals. So let f and g be integrable functions on an interval that contains a, b, and d. And let's find the integral from a to a. Well, the answer is it's going to be 0, regardless of the function is. So that makes sense because the net area in that case is going to be 0. If your upper and lower limits are the same, the area under the curve is simply a line which has no width, no breadth, no area. Okay, so for any function, that's always true. Now, here's something that's interesting. When we talk about the lower and upper limits, the lower limit doesn't always have to be less than the upper limit. What? How can that be? Well, this is a relationship. First of all, the integral from b to a of f of x dx is equal to -1 times the integral from a to b. So the only difference is we've swapped the limits of integration, and it basically changes the sign. Why is that? Well, remember in that definition, when we compute the delta x, if it's equally spaced subintervals, we've got b minus a over n, right? What happens then if I swap the limits of integration? Change them, then it'll be the opposite sign, right? If delta x, say, is, some positive quantity, then switching them will become a negative quantity. Either way, it will change the sign. So we can have situations where the lower limit is bigger than the upper limit. If you don't like that, great. Simply swap the limits. Just be sure to multiply by -1. That's all you do. Just going back to this example that we just did. Where is it? Here. For instance, what would the integral from c to b of f of x dx be? From c to b, how can we do that? All right, c to b. C is bigger than b. How does that work? Well, that's the same thing as what? Negative the integral from b to c. And we just, of course, talked about that. That integral is -7. So it's -1 times -7. It's just +7, right? Just changes the sign, right? If I did the integral from b to a of f of x dx, what would I get? -28 instead of +28. Um, the next two examples, 3 and 4, properties rather, are sometimes called the linearity rules. And these are directly coming from the linearity properties for summations. So if I have the definite integral from a to b of a sum of two functions, f of x plus g of x, I can write that as the sum of the individual integrals of f of x and g of x, or difference, right? If I have a constant multiple c times some function, I can pull that constant multiple outside the integral and just then multiply it by the definite integral from a to b of f of x dx. Can only do that for constant multiples. Property 5 says the integral from a to b of the function f of x is the integral from a to d plus the integral from d to b. So what's going on here? Let me illustrate this. Let's suppose we have some function f on the interval from a, we'll say a is here, and we'll just say b is here. And let's choose d to be in between a and b. It doesn't have to be, but this will make it clear. So look at this integral here from a to d. From a to d, right, net area is going to be this region here. Right? And then the next integral from d to b will be this region here. Let's just shade that in this way. Okay. Well, what do you know about the sum of these two integrals then? That adds together to the total area from what? From A to B under the curve, right? Which is that. And so hopefully that makes sense. The key in this property is to note that from A to B, it's the integral from A to D. D is the upper limit here, and then D is the lower limit here. So it's from A to B is what we get. So these have to match in order for this to work. Now, it turns out that D does not have to be between A and B. D can be greater than B, or it can actually be less than A, and this statement is still true. Now, Last property here, if um, let's see, the absolute value of f is integrable on the interval in a to b, on the integral from a to b rather, then the integral from a to b of the absolute value of the function is the sum of the areas of the regions bounded by the graph of f and the x-axis on AB. And what's happening there? Well, let's go back to this example here. What would the graph, if this is the graph of f, what would the graph of the absolute value of f look like? Well, when we take the absolute value for the function on the intervals from a to b and c to d, nothing changes, right? The graph is the same because the outputs are all positive. However, here, the value of the function at this point is some negative number. When I take the absolute value of that negative number, it's going to come up here, right? It's going to be a reflection in the x-axis. So the graph would actually come up and look like this, right? And now the area is beneath here, which would be positive. So in other words, if you take the absolute value of a function and you're looking at the definite integral, all these areas need to be basically multiplied by -1 to make them positive. Does that make sense? So if you were doing this function, trying to find the absolute value, the definite integral from a to d of the absolute value, you would want to know where it becomes 0 and changes from positive to negative, but you would do what? The integral from a to b, regular, plus what? -1 times the integral from b to c, because what's that going to give me? That's going to give me +7. And then plus the integral from c to d. So you'd break it up into those three parts. So let's use these properties to illustrate, or let's illustrate the properties here. Assuming I have these integrals, notice that's f of x, that's g of x, and then I have some more integrals involving f of x with different limits of integration. So given that, let's evaluate the following. Well, this first one, I'm just going to use the linearity rules, numbers 3 and 4. So this becomes the definite integral from 1 to 9 of f of x plus, well, the integral from 1 to 9 of 3 times g of x dx, but that 3 is a constant multiple, and I can pull it outside, so plus 3 times the integral from 1 to 9 g of x dx. And now we know what's the integral from 1 to 9 of f of x dx? That's 12. Plus 3 times the integral from 1 to 9 g of x dx, that is -2. 12 plus a -6 is 6. Okay, so that illustrates the linearity rules for definite integrals. What about the integral from 4 to 1? Well, man, 4 is a lower limit is greater than the upper limit 1? Well, that's possible. But do we have any integrals here that can help us? Yeah, this one right here. So notice the integral from 4 to 1 is what? Negative, remember, the integral from 1 to 4 f of x dx. So I'm making use of property number 2 at the top here. And then this is equal to -1 times what? The integral from 1 to 4 is -7. And so we get +7 there. Okay. Now, look at this one, the integral from 4 to 9. We're going to make use of property 5 here. So I don't have any one that goes from 4 to 9, but I do have, for instance, 1 to 9, and I have 1 to 4. Okay, so there's a couple of ways you can do this. I can, for instance, say this, that the integral from 4 to 9 is indeed the integral from 4 to 1, which is the one we just evaluated, plus what? So we're going from 4 to 1, then what? I can go from 1 to 9, which is another form that I have of the function. And so this illustrates that fifth property. And notice the upper limit here matches the lower limit here. And so I know that this integral plus this one will give me this one. And so based on what we just did, this one is 7 and this one is 12. And we get 19. Take a little sip here. Okay, let's take a look at the last one here. Now this one, first thing I would say is it's 2 times f of x. So let's use the linearity rules and pull that multiple of 2 out. Okay. Now, how can I use the integrals that I have to express the integral from 9 to 7? Well, obviously you've got a 7, I'm thinking this one's going to come into play finally. And I've got a 9, so at least this one's going to come into play, not the g of x one anymore, because we're just dealing with f of x only. But I'm actually going to use all three of these ones involving f of x. So one way to do this is to note that this is 2 times what? The integral from 9 to 1. You say, well, we don't have 9 to 1. Well, we do have 1 to 9, and so we know what's going to happen there, right? This will just be negative 12 for this one. Plus, now I'm going to go from 1 to 4, which is this one over here. So notice the upper limit 1, lower limit 1 here. This will be the integral from 9 to 4, but we want 9 to 7. No problem, because we'll use this last one from 4 to 7. And I'm basically using that property 5 here twice. So this will give me the integral, these two will give me the integral from 9 to 4, and then notice the upper limit here at 4, lower limit at 4, this will be 9 to 7. So it's kind of like these limits cancel in a way, these limits cancel, not really, but you can think of it that way, and this will give me the integral I need. So the answer would be, this one was negative 12, as we talked about, right? Because I changed limits of integration. The integral from 1 to 4 is negative 7, and the integral from 4 to 7 is 3. And so I get, what do I get here? Negative 19, negative 16 times 2, negative 32. Okay, so playing around with the properties of definite integrals allows us to evaluate the definite integrals giving information like the above. Now, we're finally ready for using the actual limit definition to find the definite integrals. So when evaluating definite integrals using the limit definition, we are going to use right Riemann sums, and we're going to use equally spaced grid points. Thus, we got x sub I is a plus I delta x. If you remember, that's the right-hand endpoints for each subinterval. And of course, delta x is b minus a over n, equally spaced subintervals. Then our definite integral becomes, the limit as n goes to infinity, I equal 1 to n summation of f of x sub I star times delta x, where the x sub I star, if I just replace it with this, becomes that. So this is the definition we are going to be using. These are important sum formulas that we've shared before. I think these are, well, first of all, I equal 1 to n of c is cn. And again, for example, if I sum I equal 1, say, to 3 of 4, what would that be? Well, when I is 1, it's just 4. There's no I, so it's just constant. When I is 2, it's 4. And when I is 3, it's 4. So I'm adding 3 fours up, so that's the same thing as 4 times 3 or 3 times 4, which of course is 12. But that's the idea. It's just c times n, right? The constant times whatever n is. These are the linearity rules, so I can pull out a constant multiple, and I can break the sum of a sum into the individual summations, right? So if I have the summation AI plus BI, I can write that the summation AI plus the summation BI. And then we've got the next three are the so-called power sum formulas. Now these I expect you to know. I'm not going to give them to you. These I will give you. And if you have any questions about these, I can show you where these are derived from. But this says the summation of the first n numbers, right? I equal 1 to n of I. So this would be 1 plus 2 plus 3 plus 4 plus 5 all the way to n is equal to this. Just look at this for a minute. N times the quantity n plus 1 over 2, which basically says take n, multiply it by 1 more than n, then divide by 2. So for instance, what would the summation I equal 1 to 100 of I be? In other words, what's the sum of the first 100 positive integers? 1 plus 2 plus 3 all the way to 100. We'll answer, it's 100, n is 100, times 100 to 1, divided by 2. Well, 100 divided by 2 is 50. 50 times 101 is 50, 5,050. And so the sum of the first 100 numbers is 5,050. Voila, just like that. So it's a powerful formula. And it can be shown by induction or proved other ways. Now, often when we're using this in the problems we're doing, I'm going to use this more expanded version. In other words, if I distribute the n through of n squared plus n and then divide it into two fractions, I like to use this way. If you look at a lot of people doing it, you might see them using this. That's fine. It's just when we finally take this limit here, this form to me just makes it a little bit easier, a little more work, but I like to do it that way. Now, if you sum the first n perfect squares, so this would be 1 plus 2 squared, which is 4, plus 3 squared, which is 9, plus 16, plus 25, and so on, all the way up to n squared, you have this formula. Now, this is n times n plus 1 times 2n plus 1 divided by 6, so it's more complicated. If you expand all that out and break it up, you get this. That's the one I'm going to typically use, but uh, we get this. And then sum of the first n cubes is this formula, which expands out to this. So these three I'm going to give you on the test. You don't have to memorize them, but you need to be able to use them. Okay, so let's do it. Let's do this problem here. Use the limit definition uh, of the definite integral to evaluate the following definite integrals. We'll do two of these. So you do have to use the directions, right? So we've done some definite integrals, interpreting them in terms of area. Later, we'll use the fundamental theorem of calculus, but this is definitely using the limit definition. All right, so what do we have here? We have the value of A, lower limit is 1, B is 4. The actual function that we're integrating, the integrand is x squared minus 1. And what's our delta x? It's b minus a over n. B is 4, a is 1. I get 3 over n. That's my delta x. And then our x of I stars is a plus I times delta x. A again is 1. I times delta x we just found is 3 over n. So this becomes I times 3, or 3i over n. And now let's do this. This integral is equal to the limit as n goes to infinity, summation, and you're going to be writing that sigma notation quite a bit in this process. A little bit of work there. It's f of a plus I delta x. A plus I delta x, we said, is this, times delta x. And what's delta x? It's 3 over n. Okay. So first step is to evaluate this thing. And so let's do that. This is equal to, again, the limit as n goes to infinity. Summation I equal 1 to n. So what is f of this part? What's f of this? Well, f of x is this, so I just replace x with 1 plus 3i over n. So this becomes 1 plus 3i over n squared minus 1. That's the f of I plus 3i over n. Don't forget times the 3 over n. Okay. Sorry, this looks a little bit weird. This is 1 plus 3i over n. So quantity squared. Now, all this stuff, I like to just simplify this whole thing. You'll see some people will take this 3 over n. It's really a constant multiple because the variable is I, not n. Variable is I. Now, n is going to infinity. You can't pull it outside the limit, but you can pull that 3 over n out in front of the summation sign. But you're going to have to redistribute it through the way I like to do it. And so I'm just going to do everything mathematically here. Just remember, if I square 1 plus 3i over n, what do I get? I get 1 plus 6i over n plus 9i squared n squared. So be careful. When you square 1 plus 3i over n, you just don't square 1 and then square that. It's not 1 plus 9i squared over n squared. Where's the 6i over n coming from? The outer and inner terms when you FOIL that out. So make sure you know that. So simplifying this, we have 1 Don't forget this minus 1. 1 minus 1 is 0. And I just have the 6i over n plus 9i squared over n squared times the 3 over n. All right. Now I'm going to go ahead and distribute this through here. And we write this summation over and over again. It's a lot to write. Well, let's see what we get here. 3 times 6 is 18i, n times n, n squared. 3 times 9 is 27, I squared. N times n squared is n cubed. Now, I've simplified this down. Okay, so this whole thing, f of 1 plus 3i over n times 3 over n is this. Now, we're going to make use of the linearity rules up here. So I have this expression here down at the very bottom, right, which I can split up by the summation, and then any constant multiples can come out. Now, the constant multiples are anything except for I. I is changing in the summation, right? So this can be written as the limit as n goes to infinity. Put a parenthesis here. It'll be this summation I equal 1 to n of this plus summation I equal 1 to n of this. Now this one, the 18 over n squared is a constant multiple, and that can come out, and we're left with the summation I equal 1 to n of just I. This summation, the 27 over n cubed, can come out, and we're left with the summation I equal 1 to n of I squared. Okay, so that's using the linearity rules here. Okay. And now, what are we left with? Summation I equal 1 to n of I, summation I equal 1 to n of I squared. That's where these power sum formulas come. So for instance, this one here, I'm going to use this relationship. So summation I equal 1 to n of I is this, but I'm going to use this second one, the equivalent expression. So let's write this out. So this summation I equal 1 is going to just be replaced with this. So in parentheses, because I will do one more distributing, n squared divided by 2 plus n divided by 2. And over here, what's the summation I equal 1 to n of I squared? Let's pull that over there. It's this, but I'm not going to use that. I'm going to use the expanded out version. Okay. Whew, take a little break. That's a lot of stuff to write, but a lot of algebra, but it's going to clean up because we're going to do distributive property here and distributive property here. Notice here, when I multiply these two fractions, the n squareds will cancel. 18 divided by 2 is 9. Here I got 1 n up top, 2 in the bottom, so I'll have 1 n on the bottom. 18 divided by 2 is 9. I get plus 9 over n. Here, multiply this fraction times this one. The n cubes factored, 27. The n cubes cancel, rather. 27 divided by 3 is 9. Here, I got an n cubed in the bottom, n squared on the top, so I'll be left with 1 n, and I get plus 27 over 2n, right? 27 over 2n. Here, n cubed in the bottom, n in the numerator, I'll be left with an n squared below, and I've got 27 sixths. 27 sixths has a common factor of 3. That's 9 halves, so we'll get 9 over n squared, right? Because it's n over n cubed. So there is the simplification. Now, you do not have to combine this as one fraction. Don't do anything crazy like that. Notice in this form, we're good to go because as n goes to infinity, what do we know? Obviously, the nines will not change. There's no n. But what's going to happen to these fractions? Since since it's a constant up top and some positive power of n in the denominator, these are all going to go to 0. As n goes to infinity, these disappear and diminish to nothing. And so the result is 9 plus 9, which is 18. That is the value of the definite integral. All right, that's a lot going on there. Let me just say that we can um, check our answer because there's a lot going on here, obviously, and it's easy to make a little mistake somewhere. And of course, that's going to affect everything. But I do want you on the limit definition to show all these steps clearly, but there's going to be a way to check. And let me show you that with the calculator. Now, I'm going to use the newer model calculators on this. There is a definite integral calculator built in. It's a numerical calculator, um, but it will give you the value of this definite integral. And if you have the older model, then please see me and I'll show you how to do that. So where you go is you go to the math menu, and you'll see down here, for me, it's number 9, it's FNINT, the function integrator. So we're going to go down there, hit enter, or just type 9, and you will get something that looks just like your integral. And you just plug in lower limit 1, use your arrows to move around in this thing, upper limit 4. And then here you need the function. And you can do it with any variable, but I'm going to use x just because it's easy with this x button. So it's going to be x squared minus 1, right? In the parentheses, everything there. And then the d what? Well, you're just going to put an x, right? So that's going to be the value. You hit enter and it will estimate that. Of course, we get 18, which is good because that's what we got here. So you will have a way of checking your work, and I would encourage you to do all the work like I've done here. Check in the calculator. If you're off, make sure you've entered it in correctly here, first of all. But if you're off, then you need to find your mistake. It's up to you to debug, if you will, your work. You need to find where the error occurred. Okay. All right, let's do one more example and then we'll be done. And this one, we'll do the integral from 0 to 2 of x cubed plus 4x. So again, the value of a is 0, value of b is 2. The function we're talking about is x cubed plus 4x. And we're going to have a delta x, which is b minus a over n. So that's 2 minus 0 over n. It's just 2 over n. And the right-hand endpoints, the x sub I stars, remember a plus I times delta x. A is 0, so that's 0 plus I times delta x. I times 2i, I times 2 over n is 2i over n. So there's the setup. So again, let me just reveal the what we have here. So this becomes the limit as n goes to infinity, summation I equal 1 to n, f of a plus I delta x, which is 2i over n, times delta x, which is 2 over n. Okay. Now let's evaluate f of 2i over n. What is f of 2i over n? What is f of 2i over n? Well, f of x is x cubed plus 4x. So where I see an x, I'm going to replace it with 2i over n. And I'm going to get 2i over n quantity cubed plus 4 times 2i over n. So that's, you put that in parentheses, and then don't forget times the 2 over n, the delta x there. Okay. Well, what is 2i over n cubed? If I cube it, I get 2 cubed, which is 8i cubed over n cubed. And what is 4 times 2i over n? It's 8i over n, right? So I've got those two things, and what am I going to do now? I'm going to distribute, right, this 2 over n times each of those things. So 2 times 8, 16. I cubed. N times n cubed is n to the 4th. Plus 2 times 8, 16i, n times n squared. So there's the simplification. Now I'll use these linearity rules, so don't forget them. They're right there at the very top. break it up into individual sums, and then pull out any constant multiple. So I'll have two individual sums. Remember, the constants are anything except for the I, right? I is the variable of the index of summation. Oh, sorry, I messed that up because I want to pull out the 16 over n to the fourth and leaving I cubed. This one I'll pull out the 16 over n squared, and we left with I. Okay. So let's use our power sum formulas, right? So let's see, what is the I cubed? We haven't used that one. Here's I cubed, it's this. So this becomes the limit as n goes to infinity. 16 over n to the fourth. Sorry, that was so small there. And then the summation I equal 1 to n of I cubed is this expanded fraction. N to the fourth over 4 plus n cubed over 2 plus n squared over 4. Okay. And then we did the I before. It's just n squared over 2 plus n over 2. Okay. And now we'll distribute through here and here. We're almost there. 16 over n to the fourth times n to the fourth over 4. The n to the fourths cancel. I'm left with 16 divided by 4, which is 4. Here, 16 divided by 2 is 8. I got one n in the bottom. Here, I've got two n's in the bottom, and 16 divided by 4 is 4. So there's that. 16 divided by 2 is 8. N squared divided by n squared is 1, so that's 8. 16 divided by 2 is 8, and I have one n in the bottom. And then as now, finally, we can take the limit. Notice every time, what do I have? All right, after the equal sign, a limit. You have to keep that limit all the way until the very end. So now as n goes to infinity, right, that's going to 0, that's going to 0, and that's going to 0. And I'm left with 4 plus 8, which is 12. You can check with that calculator feature that I showed you to check that that is the correct result. Okay, so I am expecting you to write this out correctly. Notice I'm using equal signs, putting it between things that are equal. I'm writing the limit sign every time until I take the limit at the end. Of course, then it goes away. And we're writing the summation every time until what? We get to where we replace those sums with the power sum formulas. You could also be using a situation where you use this relationship here. If you just have the summation I equal 1 of just a constant, if there's no I at all, it's just the constant times n. So you can simplify those sums very easily. Okay. Well, I hope this helps. These ones take a little bit of time, so please practice them. There's some homework. If it says use the limit definition, this is what you're supposed to do. Okay, hope this helps.